that also is worth mentioning is when is a Hessenberg variety Schubert, and when is a Schubert variety Hessenberg. And so Escobar, Prekop, and Shereshian have a fairly complete answer, both for type A and for type C, in terms of certain kinds of pattern avoidance. To do this, by the way, they have at a certain point to change the representation which we use to define Hessenberg varieties in general. So instead of the adjoint representation G inverse XG, they replace it with a different representation. So another question is about the intersections of different Hessenberg-Schubert varieties. So this question is partly motivated by the desire to sort of describe ring structure again, or intersection cohomology, through sort of understanding how these different Hessenberg-Schubert varieties intersect with each other. So sort of more precisely, I'm going to kind of take one of these Hessenberg-Schubert varieties and then think about intersecting with an opposite Schubert variety, and then characterizing what's happening in this intersection. So this kind of construction is related to Cauchy-Lustig polynomials in the Schubert case. So the intersections here are picking up, I'm going to pull out my spotlight again. So this is on the, I've got the full flag variety Bruja order. So what an intersection is doing right here, right? Like, so I'm picking up, so this is sort of moving one direction in the closure relation, and this piece would be moving the other direction. So I'm sort of picking up these Bruja intervals in the graph. But like here is a corresponding graph for the a different regular semi-simple Hessenberg variety. And you can see already that the sort of intervals that you get by looking at looking at the sort of flow up intersected with the flow down of the graph can be really different without those central edges. So taking one step back from the Schubert questions, what other interesting pavings do Hessenberg varieties have? So the motivation for thinking about, especially, well, Schubert pavings in general of Hessenberg varieties, the motivation for those ones was actually to think about cohomology and homology. But there's others that are interesting. So Peterson thought of paving regular nilpotent Hessenberg varieties, using the opposite Borel. And this doesn't actually give you a paving by affine cells. In fact, the intersections are generally quite complicated objects, complicated enough that, bringing back this sort of result of constants, if you take the intersection of that big opposite cell with the Peterson variety, the coordinate ring of that intersection is the quantum cohomology of the flag variety. Risch then actually proved that the quantum parameters in that quantum cohomology ring are really minors of the matrix representatives of this intersection, getting some really kind of beautiful determinantal results out of that. So I think the moral there is that, like, pavings by affine spaces are interesting, but pavings by other things can be actually quite powerful and useful. Furthermore, even within the realm of pavings, of affine pavings, Prekop's paving uses different Schubert cells. Fress presents some different pavings for Springer fibers. There is some work comparing some of these pavings. Adeyemo and Olasupo compare those Springer fiber pavings. DeWitt and Harada actually have a more extensive systematic description of how what the fillings look like for permuted Schubert cells, and what sort of effects that has. And so at the same time, one of the ways that we both construct pavings and then end up using paving kind of results is through torus actions. So a related question to the question of pavings is which tori act on each Hessenberg variety and in what sorts of ways. So for instance, within the flag variety, the torus just acts by a matrix multiplication. So here's a matrix multiplied by just the diagonal matrices. So this is not in our canonical form on the right-hand side, but if you just kind of divide out, you can put it in the canonical form in that following way. But now if we imagine that we still wanted to be in the Peterson-Schubert cell that we identified before, we would need those two red entries to be the same. So the only torus that could act in that context is a torus that preserves this sort of condition of those two entries being the same. So sort of how the difference between the full flag variety and the Hessenberg-Schubert cells is that we have conditions, and these conditions somehow need to be preserved. And since the conditions depend on both the matrix X and the Hessenberg space H, the sort of way that you would expect to see tori acting would also have a dependence on both of those features. So there are like various results in this context as well. Damari, Perchesi, and Shaman originally defined Hessenberg varieties. So they were really especially thinking about semisimple Hessenberg varieties upon which the full torus acts. And they thought a lot about the regular semisimple Hessenberg varieties. So with h of I equals I plus 1, so this we mentioned before, is associated, it's a toric variety associated to the permutahedron, or if you want to think about fans, decomposition into vial chambers. With Arata, we described a generic S1 action that applies to, well, that you can use for any, that you can use given a Hessenberg variety or given X, there is a generic S1 that acts on it. With Rebecca Golden, we recently described various X and H in which larger tori act. Abe and Crooks have results about the minimal non-zero nilpotent orbit. Their results are general type. In type A, this is sort of thinking about the matrix that is 1 in the top right corner and 0 everywhere else. But one reason why I personally would like to know about torus actions is because I would love to know when are Hessenberg varieties GKM, and in fact, what is their torus equivariant cohomology? And I'm going to say just a few words about what that actually means. So if you are a complex projective variety, if you have the action of a torus T, so functoriality tells us that the fixed points injecting into the variety induce a map going the other direction on equivariant cohomology. Through the work of many people, there's this sort of principle that for some spaces, this map is actually an injection. And Cheng and Schubert actually identify the image of this map inside the equivariant cohomology of the fixed points. And so just as the ordinary cohomology of fixed points is standard, it's like simple, it's nice, it's just a direct sum of your base coefficients. The equivariant cohomology of fixed points is a direct sum of polynomial rings, one for each element of the fixed point set. So
there's a question.
Yeah.
The question is, don't you need there to be finitely many fixed points for this? Great
question. Yes and no. So the original definition, which which I'll say in 1 second, does actually use finite fixed points and finite one-dimensional orbits. There are various kinds of extensions. It was also, for instance, originally defined to think about affine flag varieties and affine Grassmannians. So like the easiest kind of extension is that sort of infinite case that is infinite as a sort of growing union of finite spaces. But there are other extensions to say non-isolated fixed point sets and so on.
But yeah, Frank adds this is for 0-dimensional fixed points, he thinks, is that right?
This particular, so if you can wait for 1 second. Oh, the bottom slide. Yeah. The bottom slide is assuming isolated fixed point set. Isolated fixed points, yes. The bottom line in this picture.
Thank you.
And in fact, so I think would generally in the next things like to assume finiteness that can be extended, but so the moment graph of a variety is an edge labeled graph for which vertices are the fixed points, edges are pairs of fixed points that are in the closure of a particular one-dimensional p-orbit, and we have a label on these edges that comes from the torus weight on the corresponding one-dimensional orbit. So to the question, this sort of assumes that I have isolated fixed points, and if it's going to be a finite graph, then they need to be isolated and finite, both fixed points and one-dimensional orbits. So moment graphs have this name because they are the 0 and 1 skeleton of the moment polytope in symplectic geometry. So the theorem is, so the GKM theorem is from Goreski, Kotwitz, and McPherson, and it basically packages the Chang-Shelbride result, and it packages that sort of that whole equivariant apparatus in a particular special case where it sort of reduces to nice combinatorics. So if the variety is equivariantly formal, if the fixed point set is finite, if the number of one-dimensional orbits is finite, then we can get our equivariant cohomology by just basically putting a polynomial at each vertex of the graph and checking that every time you go over an edge, the polynomials at the endpoints, their difference should be a multiple of the label of the edge. So flag varieties, Grassmannians, G mod B, G mod P in general are all spaces for which GKM applies, also Schubert varieties. Here's an example of 2 possible ring elements. So I've taken my flag variety moment graph. I've labeled all of the vertices with polynomials. On the left, if you sort of look, every time you see a green edge, you should subtract the polynomials at either endpoint, and hopefully there'll be a multiple of the green label, T1 minus T2. Just quickly doing it on the left, I see that yes, that is the case. If you look over the red edges, everything should be a multiple of T1 minus T3. Yes. No, on the left, that top vertex minus the thing at the bottom is T2 minus T3. So the condition fails there. On the right, however, it still works. And you do the same thing for each different kind of edge. So on the left, not an element of the equivariant cohomology of the flag variety. On the right, yes, an element. Then multiplication and addition happens point-wise, vertex-wise. So GKM Hessenberg variety. So Abe and Crooks showed that this sort of minimal nilpotent orbit is GKM and classified the equivariant cohomology. So we, with Rebecca, we described the case when so a slightly larger nilpotent orbit. Arges and Zaldivar described semisimple Hessenberg varieties. So then, in addition, there's sort of GKM-ish results. So these are cases where we don't technically have the full apparatus of the GKM theory, but we have enough structure that we can still characterize some of the equivariant cohomology results. In the Drellick case, really using sort of using the GKM theory in the ambient flag variety. So this is a situation, so sort of semi-simple has more torus action and tends to be classic GKM theory, whereas regular nilpotent tends to be most, this is where most progress has been made for sort of characterizing cohomology. So here's some pictures. So when X is regular semi-simple diagonal with distinct eigenvalues, here's some pictures of what the moment graphs look like. You can characterize when the edges show up precisely by this second bullet point, but they all have the same fixed points. The all of the permutation matrices end up being in these Hessenberg varieties. And then as H gets bigger or smaller, depending on your perspective, then you will lose or gain edges in a systematic way. So my almost last question, all of those graphs were extremely symmetric. And in fact, the equivariant cohomology in all of those cases admits an SN representation that actually descends to ordinary cohomology. So the question is, which Hessenberg varieties also have an SN representation, or what is the largest subgroup of SN that acts on the cohomology in an interesting way? Or can you describe this representation in the sense of like explicit combinatorial decomposition into irreducibles or into whatever your favorite basis is? One of the representations that's been most studied is the dot action. So I'm going to just describe this using the action of a simple transposition. So I'm exchanging I and I+1. It's going to act on a GKM class by doing two things simultaneously. It's going to act both on the polynomial that's labeling the vertex. So there I'm just going to take my variables and act by exchanging I and I+1 and the indices. I am also going to flip vertex labels over every edge labeled Ti minus Ti+1. So if I'm acting by S1 on this particular class, I am going to look at those green edges and flip the polynomials on either endpoint of the edge. I am at the same time going to act on all of the indices. Wherever I see a 1, I'm going to replace it by a 2 and vice versa, and 3 stays the same. So this is the class that I end up getting. Okay. So then I'm going to talk just a moment about the Stanley-Stenbridge conjecture. So we heard about this in a previous talk. So we've got the chromatic symmetric function of the incomparability graph of a particular kind of poset. And the conjecture is this symmetric function is a non-negative linear combination of elementary symmetric functions. So the conjecture can actually be proven if you only consider interval unit orders. Suresh and Walks studied this quasi-symmetric function coming from these unit interval orders. They noted this is bijective with Hessenberg functions and conjectured that the representation that they were looking at is the same as the representation on the cohomology of regular semi-simple Hessenberg varieties, actually the same as that dot action that we were just looking at. So Brosnan and Chow then proved this. What is the takeaway? The takeaway is that if you could find a basis for the GKM cohomology of regular semi-simple Hessenberg varieties that is permuted by the SN action, then you would have a proof for the Stanley-Stenbridge conjecture. And there are various work right now, active work thinking about how to construct these sort of permutation bases. So my final question is, which of these results holds for other Lie types? And I think I've sort of alluded at various points to some kinds of results. So precup has a general, her paving is in general type for some X. Drellick has this lovely Monk and Giambelli for Peterson varieties of classical type. Abe, Horiguchi, Masuda, Mirai, Sato have a presentation of the Hessenberg variety for regular nilpotent in types B, C, and G using hyperplane arrangements. Springer theory itself is type independent in many cases. I'd say that in general, much of the work that's been done outside of type AN comes from a very Lie theoretic perspective. But at the same time, so if you look at the book of Collingwood and McGovern, the nilpotent orbits also have this sort of beautiful concrete tableau description. So I think there's a lot of space there for some descriptions that build not from the sort of Lie theoretic perspective, but rather that are sort of describing that are deepening some of the tableau combinatorics related to types B and C. And that is certainly true of Drellick's result. So I think said all of that. I'm done. Thank you.
All right, are there questions for Julianna? Oh, okay, Maria's just typing them in the chat. Great.
Yeah.
Julianna, do you want to read them so that the—
Yes, sure. Great. Oh my gosh. They're coming too fast to read. Okay. Oh, right. Okay. So
but Julianna, let's read it out loud.
Let's go one at a time. Yes. So question one. Regarding question one, what do the PWs look like in the Springer case? Are they the images of the Schubert polynomials under the natural quotient map from the co-invariant ring to the Garcia-Purchesi modules? So I believe the answer to this is yes. So I think there is a construction where you can get Schubert classes. Well, so I guess let me be like a little bit more careful there. I don't know if the classes that come from the paving. Oh my gosh, sorry, my screen share disappeared. Can you still see me?
We can still see your screen.
Great.
And you.
Oh, and you can see my screen share. Great. So then, got it. So, all right. So you can still take, so you can do exactly, Maria, what you are saying, taking Schubert polynomials and go from the natural quotient map from the cohomology of the flag variety to the Garcia-Purchesi characterization of the, or you can mod out by the Tanasaki ideal and move into the cohomology of the Springer fibers. So I don't think I know whether those are the same classes as the paving that I would create geometrically. But I don't think, so I don't think there's a characterization of the structure constants in the Springer case. Yeah. So question two. Okay, question two. Regarding question five, I think I heard you say that the structure is related to Cauchy-Lustig polynomials in the Schubert case. And the question was, did I mean the Springer case? And if not, what is the Schubert case referring to? Yeah, I actually, so what I was trying to say is that Cauchy-Lustig polynomials are encoding intersection cohomology of Schubert varieties. And so that the intersections, intersections in that sense are capturing are capturing the intersection cohomology. Did that answer those questions? Yes, great.
All right, other questions? Yeah, Maria, if you have another question, that's fine. I don't see any other questions, so go ahead. All right, Maria promises this is the last.
Oh, yeah, no, that's a great question. So regarding question 10, is there a BCD analog of the Stanley-Stanbridge conjecture that we might want to look out for? I mean, you know, I suppose from one point of view, the construction of this representation is, and so the Hessenberg varieties in other types is like, you could just describe this completely. You can construct that dot, representate that dot action is type, it's like not even BCD, it's like type unspecific. So maybe one way to say what the Stanley-Stanbridge conjecture is in general type is something like that the representation that you get there is right, like that it is positive in terms of the basis, so that it should have some, so that it's got like a vile acting basis. Sorry for my words. Oh, Alejandro. Yeah, right. Alejandro asks about questions 8 and 9. Does it make sense to extend the action of Sn to the moment graph and not just the zero? So do you mean, does it make sense to extend the action of the moment graph, moment polytope? Great, okay. Does it make sense to extend the action of Sn to the moment polytope and not just the one skeleton? Well, I don't know what that, so the reason why I just use the moment skeleton is that's what encodes the equivariant cohomology. So I don't know, so there's no additional cohomological information that comes from the entire moment polytope. So I don't, but if the question is like, what sort of interesting actions exist on the moment polytope, like that's a separate question, maybe one that I don't know the answer to. And Travis asks if Hessenberg varieties are smooth. I'm sorry, I have a teenager, like you're hearing bings because I should have blocked my teenagers, like sending panicked text messages about the internet.
Oh, we can hear that.
Great. Okay. Are Hessenberg varieties smooth? Is there a notion of parabolic compositions like there is for Schubert varieties? Parabolic decompositions. Great. So Hessenberg varieties in general have so in general most of them have many components. So like on some level, definitely not smooth. So the question that sort of makes sense is think about the components. Are they smooth? And the answer there, I'd call this like one of the big questions. So the answer is sometimes yes. And probably most of the time, mostly not. But there's sort of very limited, there's limited information about that, and limited information about, like, I mean, even in the Springer case, there's not a complete answer of Springer fiber for X is singular if and only if the following things apply. So and in general, I guess what I'd say happens. So there are some results. So the way that parabolics tend to play with Hessenberg varieties is more. The things that I know most for parabolic, for how parabolics are used, thinking about Hessenberg varieties is more in the context of the Hessenberg space H. So to take a sort of parabolic, H to break down into one piece to do some sort of analysis over there, and then to combine the whole information back at the end. It's not, it tends to be a sort of strategy that works in some cases, but somehow, again, the sort of the classic and super interesting Hessenberg space that consists of the negative simple root spaces is very not parabolic, and so like actually tends not to be super. It tends not to be super easy to use sort of that parabolic structure on Hessenberg spaces that have the negative negative simple root spaces, the h of I equals I plus 1 cases.
All right, any other questions?